Ultimately, the body is going to turn into a skeleton. And once it's a skeleton, it's very difficult to get good information, because bones, after all, are bones. One test that can be done is to look at fluorescence. Fresh bone will fluoresce under UV light. Old bone, maybe more than 100 years old bone, will no longer fluoresce. And this is very useful because if bones turn out to be more than 100 years old, then you can be pretty safe in assuming that anyone associated with that event is also going to be dead by this time. You can do some analysis to get some more information. And what we can do is use techniques of elemental analysis to measure the level of specific elements in the bone, and this can enlighten us a little more. This is typically called fun analysis after 3 elements: fluorine, uranium, and nitrogen. Now, fresh bone contains proteins. All proteins contain the element nitrogen. And in fresh bone, if you analyze it, you will find that bone is about 4% nitrogen by weight. However, let's suppose the body is in a grave or somewhere, exposed. The proteins in those bones will gradually break down with time. And as the protein molecules break down, the nitrogen-containing compounds will diffuse out of the bone into the environment and be lost, which means that the bone nitrogen content will decrease with age. Now let's turn to the other 2 elements, fluorine and uranium. These 2 elements are not naturally present in bone. So the content of these 2 elements in fresh bone is 0%. There shouldn't be any fluorine or uranium in your bones. Now suppose those bones are buried in an area where the groundwater contains appreciable amounts of those elements. Okay, they would be leached from the local rocks. Then the bones will absorb those elements from the environment. And that means that the concentration of fluorine and uranium will increase with time. Now, you cannot use this as a kind of clock to determine time of death, because the absorption of these elements depends on their presence in the local environment. So if that body is in a place where the local geochemistry means there is no uranium, then of course it will not absorb any uranium however long you leave it. But if it's in an area where there is uranium naturally present as a trace mineral in the rocks, then you will get uranium absorption. So you can't use it as a clock, but you can use it to compare 2 bones from the same place. And if those 2 bones have been in the same place for the same length of time, the same number of centuries maybe, then they should have the same amount of uranium and fluorine. Here's an example where this kind of analysis proved critical, and this is the story of Piltdown Man. If we go back about 100 years or a little bit more, one of the great scientific challenges was finding the ancestors, our own ancestors, the ancestors of Homo sapiens. Now the Germans had found the remains of ancient humanoids, and this is Neanderthal man. The French had found the remains of ancient humanoids as well, and this is Cro-Magnon man. And since then, of course, we also have Peking man and Java man and all the discoveries in East Africa. But 100 years ago, British paleontologists were very disappointed because they had not been able to find any ancient humanoid remains anywhere in Britain. So they had nothing to compare with the remains found by the Germans and the French. Well, one dig that was going on was at a place called Piltdown. It's a little way outside London, and this was during the period 1912 to 1915. And alongside many, many bones of prehistoric animals, they also found 2 fragments of humanoid bone. And they claimed that these were approximately 500,000 years old. And so, of course, they went to the Natural History Museum in London, and they were displayed in pride of place. Now, what they'd found was 2 fragments of bone, and you can see the reconstruction in this picture here. What they found is the 2 dark parts. You can see a skull fragment, and you can see a jaw fragment. And when you look at these fragments, you conclude that the skull fragment is very similar to a modern human, whereas the jaw fragment is more similar to a modern ape, which indicates that in evolutionary terms, our brain case evolved before our jaw evolved. And this finding was never completely accepted by the community, because the more favored theory was that the jaw evolved in advance of the brain. Nevertheless, those bone fragments were there in the Natural History Museum until the late 1940s. By the late 1940s, chemical techniques had improved a lot, and someone had the courage to go to these bone fragments and do a little bit of chemical analysis. In fact, he analyzed them for fluorine and nitrogen. And this is what they found. The skull fragment turned out to be 0.2% fluorine, whereas the jaw fragment had essentially no detectable fluorine, or almost no fluorine. That means that the 2 pieces of bone had not been in that site at Piltdown for the same length of time. Therefore, they could not come from the same individual. They had to come from different individuals. What's more, the jaw fragment turned out to contain almost 4% nitrogen, which meant that the jaw fragment must be essentially a modern piece of bone. Well, it turned out that that jaw fragment actually had been taken from a modern orangutan, whereas the skull fragment was human, and it was a few centuries old. And it was a hoax. Someone had acquired these 2 bone fragments, had chemically dyed them so that they're the dark color that you see in the picture, and therefore look old, and that person had placed them in the excavation so that they would be found by the paleontologists. Well, it's never been proved who did it. There are suspicions about who might have done it, but of course after this length of time it's never been proved. But Piltdown Man stands as one of the most famous examples of a scientific fraud, but it's a scientific fraud that's been exposed by chemical analysis. What if the human remains that have been found are really old? What technique can we use for dating them? The answer is a technique called carbon-14 dating. Now, the element carbon is ubiquitous in living organisms. It's the basis of all life on Earth. Now, carbon comes in 3 forms. By far the most common is carbon-12. This is the isotope carbon-12. So in carbon-12, the nucleus of the atom is made up of 6 protons and 6 neutrons, and it's a quite stable nucleus. The very small amount of carbon is carbon-13, and in carbon-13 the nucleus of the atom is made up of 6 protons and 7 neutrons. And again, this is a perfectly stable atom. But there's a small amount of carbon-14. And in carbon-14, the nucleus is made up of 6 protons and 8 neutrons. And this is an unstable nucleus. That means carbon-14 is radioactive. And if you have a sample of carbon, which contains 12, 13, and 14, gradually, slowly over time, that carbon-14 will decay and disappear. Now, radioactive decay occurs at a very fixed and regular rate. And for carbon-14, we know what the rate is, and we measure the rate by the so-called half-life. The half-life is the time it takes for half the atoms in your sample to undergo radioactive decay. For carbon-14, that is just over 5,000 years. So in 5,000 years, half your carbon-14 will disappear. In another 5,000 years, you'll be down to a quarter. In another 5,000 years, down to an eighth, and so on, and so on, and so on. Now, how can we use this for dating? The key assumption is the amount of carbon dioxide, which is carbon-14 in the atmosphere, is approximately constant. So carbon-14 is produced by the bombardment of the atmosphere by cosmic rays. As long as the bombardment by cosmic rays is constant, then the formation of carbon-14 is going to be constant. Now, where does the carbon-14 go? It's present in the atmosphere in carbon dioxide. So whenever a plant absorbs some carbon dioxide from the air, it absorbs that amount of carbon-14. And that carbon-14 will then make its way through the food chain and end up in herbivorous animals, carnivorous animals, us, anything made of wood, etc. So we continually intake small amounts of carbon-14 from the diet, and of course we give out carbon-14 when we breathe, which means it reaches a steady state. So in a living organism, the amount of carbon-14 is at a steady state during life. But of course, when you die, all this stops. But the decay of carbon-14 through radioactive processes doesn't stop, so after death, the amount of carbon-14 drops with radioactive decay at a very nice and fixed mathematical rate. So William Libby, who won the Nobel Prize in 1960, developed this as a dating method, and he was able to calibrate it against historical objects, so we can have a great deal of confidence in this method. The limitation on carbon-14 is that the object you're studying must be more than a few centuries old, more than, say, 400 years old. And the reason for that is very simple, because if something is only 100 or 200 years old, the amount of carbon-14 that has decayed is too small for us to measure accurately. So if something is 500 years old, then we can get a good measurement. If something is 10,000 years old, we can also get a good measurement. Future archaeologists are going to have a problem, and that is because the assumption of the carbon-14 in the atmosphere being constant has now broken down, and this is due to testing of atomic bombs in the atmosphere back in the 50s and the 60s. Those atomic bomb explosions produced all sorts of isotopes, including carbon-14. And you can see on the graph here that prior to atom bomb testing, the carbon-14 level was nice and steady. And then it jumps up to a big spike because of atom bomb testing and is slowly dropping away. But it's going to take some time for it to get back to normal. What's this got to do with forensic science? We're talking about things here that have been dead for centuries and centuries. Well, let's look at the story of Peter Reinbart. It was suspected that Peter Reinbart murdered his wife Malika back in 1960. But there was no evidence. More to the point, there was no body. Her body was never found. It was suspected that Reinbart had buried her body in this place called Lindo Moss, and this is a peat bog on the edge of Manchester. Now, peat is formed when the vegetation of the bog is compressed, and traditionally in Northern Europe, peat has been used for centuries, particularly for fuel. If the peat is dug out, it's cut up and dug out and dried, it can then be burned as fuel. So in 1983, a man was doing just that. He was peat cutting when he found a skull fragment. An examination of the skull fragment showed it still had tissue attached, even brain tissue, which of course indicates it must be quite recent. So this was handed to the police. The police went to Reinbart, confronted him with the fact that they'd found this fragment. Reinbart confessed, and he was convicted of murder and sent to prison. Then someone had the idea of sending that fragment to Oxford University for carbon-14 dating. And when the results came back, it must have been quite a surprise to Peter Reinbart, because it turned out to be nearly 2,000 years old. It wasn't from his wife after all. But what is surprising is that it's 2,000 years old, but it still contains tissue. How can tissue survive that period of time? And the answer comes in the very unusual chemistry of the peat bog. So on the left there is lindo moss. It's a peat bog, and as I said, peat is formed by the compression of this vegetable matter in the swamp. And the vegetable matter, as it breaks down, releases chemicals into the water. Most particularly, it releases tannins. And this is why the water on peat bogs is often a brown color. It's the same chemicals that make tea brown. And in fact, they taste about the same too. So the peat bogs are acidic, and also these tannins have antibacterial properties. And that means that the microorganisms which are responsible for the tissue breakdown can't grow. Their growth is inhibited by these natural antibiotics, the tannins. Now, it's not true for all peat bogs. On the left there you have lindo moss, where that skull fragment was found. On the right is Dartmoor. Dartmoor should be well known to all of us because quite a few of the Sherlock Holmes stories are set on Dartmoor, most famously The Hound of the Baskervilles. The Dartmoor chemistry is quite different. Dartmoor has 20,000 archaeological sites, and that's one in the picture. Many of those archaeological sites are graves. That one is a grave. The depression in the center of that stone circle is where the body was buried. And yet, there's been almost no human remains found on Dartmoor. The chemistry there is a little bit different. The human remains dissolve away. Now, peat and peat bogs are not restricted to England. They're spread all across northern Europe, northern Germany, and especially Denmark. And as people have been cutting the peat for fuel and for other reasons, they've been finding bodies in the bog. And these bodies typically are extremely well preserved, and they date back to about 2,000 years ago. And they are from the Celts. The Celts were the people living in this part of Europe at that time, and they, it is believed, practiced human sacrifice. And what they would do is they would ritually kill the person involved and then drop their body in the bog. What they didn't know is that body would be preserved for thousands of years. So here's one of them. Here's Grauballer Man. He was found in Denmark. And you can see remarkable preservation. That may be his original hair color. It's not his original skin color. That is a result of the tannins. And typically what used to happen when bodies such as Grauballer Man were found by the peat cutters, they looked so well preserved that the peat cutters would assume this was a murder case, and they would call the local police. The local police would come and they would take a look, and then they would call the university, and the professor specializing in this would come over. And in fact, in Denmark, they have a museum dedicated to these people. One bog person has been found in lindo moss, where Reinbart is believed to have buried the remains of his wife. This is Lindo Man, and if you happen to be in London, you can go to the British Museum and take a look at him. Well, let's end this lecture by looking at the oldest body in the world. And this is Ötzi, who was found in the ice high up in the Alps. And he was found high up in the mountains by a pair of hikers. And what had happened is that the warmer climate had caused a lot of snow and ice to melt, and his body had become partially exposed. Well, when he was seen by these two hikers, they of course assumed that he was a recent accident victim, and they called the local authorities. And then of course it was realized he wasn't a recent accident victim. He had actually been up there in the ice for many, many years. And it turns out that he had died up there in the mountains 5,000 years ago. His body had been covered in snow, encased in the ice, and it had been preserved for 5,000 years. And many of his possessions, such as the axe he had with him, his clothes, were also preserved. We don't know why he was up in the mountains. We do know that he was injured. There's an arrowhead buried in one of his shoulders. But we also know that he found a rather curious place to die. When these two hikers were hiking in the mountains, they thought they were inside Austrian territory. So when the body was found, it was taken to Innsbruck in Austria for further study. It was only later that someone realized that he had actually crossed by a few meters into what is now Italian territory to die. So the Austrians had to hand him over to the Italians, and now he's in a museum of his own in Bolzano, Italy. So Ötzi is believed to be the oldest body in the world, preserved by the ice and snow of the Alps. Well, in this lecture we have looked at many different techniques that can be used to determine time of death, depending on how long the victim has been dead. We've looked at rigor mortis, alga mortis, and liver mortis, which last for a day or so, or 2 days. We've taken a look at some of the circumstantial evidence that can be used and will be increasingly used. For bodies that have been dead a bit longer, we can look at the state of putrefaction. We can do some entomology with the maggots. And then getting into more historical archaeological territory, we have fun analysis, we have bone fluorescence, we have carbon-14 dating. But all the time, whichever technique we use to determine time of death, we have to understand that it can be affected by external environmental factors, so all of these estimates are subject to errors of one magnitude or another.